So what we'll do today is discuss the subject of sensitivity analysis, which is in chapter 16 of your book. Broadly speaking, what this subject is concerned with is the relationship between the parameters in the Bayesian network and the conclusions that you draw based on this Bayesian network. You're going to see there is different aspects of this relationship. It's very important practically. And in a sense, it is now even more relevant given recent interest in explaining AI systems and trying to find out why they're doing what they're doing. So what we're going to do is motivate through a concrete example. Here's a Bayesian network known as ALARM from medical monitoring. And if you look at this network, let's take here a close look at a few variables. So you look at this variable here, HR, and we have evidence on it that it's slow. And let's look at this variable as well, where we're computing the posterior. So this is the posterior given that particular evidence. And now let's look at this additional variable here, which only has one parent, right? So what we're going to do next is open up the CPT for this guy, so we can look at the parameters and make a change to one of these parameters. So here's the CPT. Suppose in this case we go ahead and do a change to this distribution here, right? So it was 98, and the probability now is 96%. And now we're going to pose a few questions that will exemplify what we're going to do with sensitivity analysis. First question is, if you made this particular change, you probably want to know how will this parameter change impact the value of an arbitrary query of the 4 probability of y given some evidence. Now, you can go ahead and do the change and recompute everything, but the idea is we're going to try to do that without doing inference by putting some kind of bound on arbitrary queries as a result of making that particular change. So think of this as, again, saying, I made this particular change to this parameter. Can you give me any guarantee on the stability of answers I've obtained? Will this just turn things upside down? Or can I bound it in some way? And you're going to see that you're going to get some nice answers to this question. By the way, before I move on, let me just mention that all of this chapter 16 pretty much was the work of one of our graduate students, Chan, who did his PhD thesis on this subject. All right, so this is the question that we will be concerned with, the first question. And in this particular case, the question, for example, could be, how will this particular parameter change impact this particular probability, right? The fact that, this distribution given that. Once more, without doing inference. You can always do the change and rerun inference, but we want to do this without actually doing inference. Okay, so here's another question. In this question, you look at this query result and say, okay, according to this, the probability here is 69%, right? So the probability of this being low, given that that is being low. This is the evidence, this is the query. But suppose someone who's familiar with this situation, a physician, looks at this and say, no, in this case, this should be at least 75%. And then in that case, you say, well, how do I do that? What aspect of the model should I change so that the probability ends up being greater than 75%? And we're assuming here we're only changing parameters. So again, the question, how do we efficiently identify minimal parameter changes that can help us satisfy this query constraint? And we're going to see other constraints. You've seen this particular style of queries before and you played with it. Again, you'll find that this will have a very nice and elegant solution. And the third kind of question we're going to look at is relate to getting a feel of how much of a change did we do. So here's one example to motivate this part. Suppose for the previous question, you get a whole bunch of recommendations, right? So these are all changes that if you make will satisfy the constraint. And I'm talking here about changes being made to different parameters. So if you look here, for example, it says look at the first row. This is the current value, and I suggest that you change it so that it's less than or equal to that. If you do that, then the constraint will be satisfied. And here's another suggestion and so on. So there are multiple parameters in your model, and changing either in this case, according to what's specified, will satisfy your constraint. You may want to get a feel of how much of a change I'm making. Now, measuring the amount of change turns out to be interesting in the sense of how do I measure change? Do I look at the absolute change? Say, here's the parameter value now, here's its next, and take the difference. Do you look at the relative change? And as it turns out, that neither of these is what you want. And you'll see later what turns out to be a more interesting way of measuring change. So it's going to be something else. Just to prepare you for that part when it comes. Whether a certain way of measuring change is good or bad, in this case, depends on whether I can relate the change to the parameter to the change to a query. So for example, can I bound the absolute change in a query by the absolute change in a parameter? Turns out not. Can I do it if I look at the relative change? Turns out not. But there's another way of measuring the amount of change where you can actually bound the change to the query in terms of the change to the parameter. And this is going to be one of the nice outcomes that you're going to see today. All right, so here are the three questions we're going to be looking at. One of them, you can think of it as talking about from local to global belief changes. Local means parameter change, global means query. So in this case, how will a parameter change impact the value of a query? That's one of the questions we're going to be looking at. And the second thing, you can look at it as from global to local belief change. And this is when I come and tell you I need a certain constraint to hold on global beliefs. What kind of changes can I make to the parameters so that I can attain that? And again, we've seen concrete examples of both. And the last one is quantifying belief change. How do we choose the smallest change among several candidate parameter changes? And for that, we have to have a notion of smallest or a notion of change. So basically, the lecture today is 3 segments, one for each one of these guys. That's what we're going to be doing. And once more, you're going to see the math is beautiful and the results are super elegant. And they're all implemented. I think almost everything's implemented on SAM-IM. Some sense of applications for the first question. Now we can estimate new query results of parameter changes, but without redoing inference. So this is a quick way of saying if I make this parameter change, then my queries stay within these ranges. The second one is mostly for debugging, basically of models. And the last one you'll see that you can potentially use to make changes to a Bayesian network, which makes it approximate, but potentially simplify inference on it, while still guaranteeing that you have not went too far off from the actual answer. You'll see, and if we didn't discuss these techniques, but sometimes people show that if you take certain CPTs and change some parameters, so you make them equal, even though they're slightly different. If you make them equal, then you can make inference run faster. But now you don't have the exact model, you have an approximate model, but I can use these techniques and say, by the way, the approximate model will be that close to the original, and we'll be able to quantify this as you will see later. Okay, so now, the math behind this is all based on this notion of interpreting a probabilistic graphical model as a polynomial, which we've done when we talked about circuits. I'm going to review this quickly in a couple of slides because it's so important. And we will not do the derivations of the results that I'm going to show you later, but hopefully once now I show you again the polynomial, you'll see why this would be standard manipulations. So if you recall from our discussion, I think that was chapter 11, maybe, the arithmetic circuits. You give me a Bayesian network, and in this case we have 3 nodes, A, B, and C, and these are the parameters. As you know, this could be theta A, theta not A, 2 of them, and there are 4 of these and 4 of these for all different combinations of C and A. being true and false, and similarly there. If you look at the distribution that's induced by this Bayesian network over 3 variables, here we have all possible combinations of the variables ABC, and here you have the probability of that particular instantiation, right? So we know this. For this guy, for example, it's theta A by B given A and then C given A. That's what you have here, and so on. Okay, that's the standard semantics of Bayesian networks, and then we introduce the evidence indicators, as we discussed earlier in the lecture on arithmetic circuits. And then we added these guys up. So the idea is we get this polynomial representation of the distribution of this Bayesian network. And here's another example. And if you remember, when we discussed the network polynomial of a Bayesian network, the observation was that each term in this polynomial, sometimes also called the monomial, has n theta and n lambdas, where n is the number of variables in the Bayesian network. So there's 4 of them here, and you can see 4 lambdas and 4 thetas. And the other observation is that all of these had exponent 1. So this was a multilinear function. And if you compute the partial derivative, basically, of the polynomial with respect to any of these guys, you will get a constant if you have the value of these things. And that actually is responsible for a lot of results you're going to see later. Okay? And you're going to see computing the partial derivative of this polynomial with respect to these thetas is the essence of most of what's going to happen later. Okay. All right. So let's now move on. Okay. Well, before we move on, let me just, since we're on this slide, show you this last example. So this polynomial represented the distribution in the following sense: that if you come and give me a piece of evidence, in this case B is true and C is false and D is true, then I can evaluate this polynomial and get the probability of that particular variable instantiation. If you remember, it was very simple. I end up setting the indicators to either 0 or 1, depending on whether they're compatible with the evidence. So A is not mentioned here, so both this indicator and that gets the value 1. And then for B, you can see what's happening here. B is 1, not B is 0. And the same, here for C, and this is for D. Right? So if an indicator is compatible with the evidence, it's a 1, otherwise it's 0. So if you evaluate this guy with this particular lambda settings, you get this, which happens to be the probability of that particular piece of evidence. So this is a representation of the distribution. And once I have this guy, I don't need the probabilistic graphical model. Again, this was done here for Bayesian networks, but the same thing applies for other types of graphical models. Okay. Let's now get to the 3 questions that we posed earlier and see how we're going to do these. And we'll start with actually the second question, the one from global to local belief change. That is, I give you a constraint on some query of the form probability of y given e, and then I want you to look up for parameter changes that guarantee that. And here's the concrete example. We set evidence on this variable, we computed the posterior on that, it turns out to be 69%, and someone says, no, I want it to be at least 75%. And what I want to do is identify parameter changes or minimal parameter changes that will do this. And the focus here is doing a single parameter change, right? So we'll talk about multiple parameter changes briefly towards the end. All right. More generally, what we want to do is find parameter changes that allow us to satisfy either of these constraints. The example we've looked at is number 1. I have some query y given e. I want it to be greater than or equal to some epsilon. But in principle, you're going to see whatever I'm going to show you will work also for these kind of constraints. You pick up 2 different variables, y and z, and you compute the posterior on each, and you want to say that the difference is greater than a certain amount or the ratio is greater than a certain amount. Right? So we're going to do number 1, but basically the same thing applies for the other 2 types. And here's something you have to realize, that let's say you're talking about a particular variable x, right? And this is one particular value of that variable x, and therefore a particular parameter. If you change this parameter, you must change the other ones for that particular variable, because they always have to add up to 1. And in this case, let's assume that the variable is binary. So what we'll do, the way we're going to handle this is we're going to introduce a meta parameter. Let's call it tau x given u. And then we're going to say that this guy is that, and this guy is 1 minus that. So now by changing this guy, we're basically simultaneously changing these ones so that they end up adding up to 1. And we're going to talk about changes to this particular guy. Now, if you have a binary variable, then making changes to a parameter, the change to the other parameter is fixed. Now, if you have multiple values, then if I change one of the parameters, that you could change the others in multiple ways, right? And still add up to 1. We're not going to do it here to simplify things, but in your book, you'll see how that's handled. You have to choose a way of how to change the others. And there is one way that you would want to do is, so again, let's say that I have 3 values, and then you change by 0.1. You add 0.1 to one of the parameters. You have to subtract 0.1 from the other 2. And what you'll see in the book, the approach is I do that while keeping the ratios the same. And but in this case, we'll just focus on binary variables. Okay. The key would be to try to compute this derivative, this partial derivative of the evidence with respect to that particular guy. And now I will show you basically a closed form or a simple form for this derivative, and will also be the basis for realizing how efficient this turns out to be. Here it is. I want you to stare at it. What we're doing here is you have a Bayesian network and you have a piece of evidence E, and therefore you computed this probability of that particular evidence. And now you're going to say, how would that probability of evidence change if I perturb tau? And this is the derivative. Now, look at the notation alpha sub E. Why? Because in the equation I'm going to show you in the next slide, we're going to evaluate alpha twice for different pieces of evidence. So we're indexing it by the piece of evidence that I have. Look here. What is this? This is a quantity we celebrated in a number of times before. That's a family marginal. And if you remember, these are the quantities, for example, that estimation algorithm, parameter estimation algorithm needed. And these are the quantities that you get, for example, as a side effect of running the joint tree algorithm or by doing circuit inference using circuits. So you evaluate this marginal, you divide it by this, another marginal. Now x prime, you divide it by this. This guy gives you this derivative. So in a sense, if you run the joint tree algorithm on the Bayesian network, or if you do circuit inference based on an arithmetic circuit, these guys are readily available, these particular derivatives. Okay, now you're going to see in the next slide how we're going to utilize this to solve this particular problem. What I would like to do is, I had a probability distribution with PR, and now I'm making a change to the parameter tau, or to tau, and then I'm getting a probability distribution PR prime. And I want this probability to be greater than some epsilon that you give me. And so the question is, I need to change the meta parameter, this guy, by some delta to ensure this. And it turns out that if you just plug things in and move them around, that's what you want. You want this relationship to hold. Look what's happening here. This is a probability of some piece of evidence with respect to the original Bayesian network. That's another one. Epsilon, you gave that to me. What is this? Partial derivative. What is this? Partial derivative. There's only one unknown here, which is this guy. So you want to solve for this. All right? And it turns out that this has two forms of solutions. It could come out to be, I want this delta to be less than or equal some number, or I want it to be greater than or equal to some number. Those are the two forms of solving this. Sometimes the solution you get for delta will lead to changes outside the range of 0, 1. When that happens, that means you can't do this, or that parameter is not relevant to this. And what you want to do generally, and that's what happens in SAM-IAM when you do sensitivity analysis, you want to run this for every parameter. And what you're going to find is some of these parameters will lead to invalid solutions. That means they're not relevant. They will not help you satisfy the constraint. And the ones that you actually leave to valid solutions will be the ones you are after, right? So it turns out to be pretty nice and elegant in this case. And what's the complexity? You get this for free. If you run inference, you got the derivatives. And the one I showed you on the previous slide is very easy to solve. So you can actually do this as a side effect of doing inference. That's fantastic. And we've seen an example of this earlier. Right? So it all relies on finding that nice form for the derivative, and the rest is basically relatively simple manipulations. All right, so let's see this in action. You've seen this example before, and now you're seeing what's happening underneath. You've got this Bayesian network that has these 5 nodes, and the parameters in this case that we're interested in are the ones for the tests, blood, urine, and scanning. And as you know, that these parameters are interpreted as either first positive or false negative rates. And in this particular example, if you recall, I did 3 tests, and the blood test came out negative, the urine test came out negative, and the scanning test came out negative, and then the probability of pregnancy was about 10%. It was 87%. This is an artificial insemination procedure. This is the prior on success, and now 3 negative tests led to dropping it to 10. And the idea was that this is not good enough. 3 negative tests should preclude the pregnancy even more strongly. And if you recall, when we did sensitivity analysis, we opened up the sensitivity analysis box, which you get from this icon there. And then we said, probability of pregnancy currently at 10%, I want it to be no greater than 5%. And when you ran sensitivity analysis, you got 3 recommendations. And if you recall, 2 of these we did not pay attention to because one of them talked about the prior of the or the success rate of the procedure. The other talked about the relationship between the progesterone and pregnancy, which were not under our control. So we only looked at this guy here, which basically suggests that we get a better scanning test. And it said that the false negative is currently at 10%. You basically need it no greater than 4.6. And if you do that, then you will get your 5% here. And if you remember, the highlight also from this example was that the other 2 tests are not present. They will not allow you to get this result. It doesn't matter how you change the false positive or false negative of these 2 guys. And now you see what's happening underneath and how SAM-IAM was able to get these results. On this first part, I want to say one more thing quickly, which is actually pretty interesting, but we'll just skip the details, and you can find these in your chapter 16. It will be with respect to this example. There's 2 parts to this example. First is just a continuation of what we just said, and the second part is what I intended to say. So I think I showed you this example in the first lecture of this course. This was about a power system at NASA Ames testbed called ADAPT. And this would be kind of a schematic. And the idea here is you're going to reason about power systems for the purpose of monitoring and diagnosis. You have all kinds of sensors. And here's an example of a Bayesian network fragment for this kind of a system. You're basically reasoning about whether there is current or power and various touch and sensors and so on. You can see an example of the sensors on this side. You can issue commands, and you're talking about the health of various components and so on. And the example here was that I have some evidence. I did close something, and then I'm getting readings, and I'm getting here this conclusion that what is the current on one of the wires, and then it's actually high, about 98 in this particular case. The question was how robust. I'm making a decision on whether there's power or not, or whether there's current or not. And in this case, the conclusion is that there is no current. And the question is how robust is that against parameter changes? So one way you can do this is by asking the question, what does it take to reach a different decision? I will make a different decision basically if I end up getting the probability greater than or equal to 50%. It's currently around 1 something. And look at this. You get to see the conclusions made. For example, look what is pointed to here. You need to get a probability that's 100 times smaller for this to flip. That's pretty interesting. Okay, so this is just one more example on what we just did, but the reason I brought this example because I want to tell you about something else you can do here, which we're not going to cover, and this is sensitivity analysis for MPE. You know what MPE is. Because you give me some evidence and say what's the most likely state of the system, and then I compute that for you. I give you a guy. I give you an instantiation. And the question here is, if this is now number 1 in terms of probability, what would it take to flip the most likely scenario? And turns out that there is also a very nice solution for this. It's in your section 16.23 in your book. Check it out. In fact, it is even more intriguing mathematically. You'll see why. But anyways, we're going to skip it, but it's also should be implemented in SAM-IM. And here's an example for the same network where we computed the MPE, and it turns out to be this. And then you ask what would flip this most likely scenario, and you also get recommendations on parameter changes, which will tell you whether this is a robust conclusion or it's something that can be easily changed based on parameter changes. All right. Okay. So this is the first component of our discussion on sensitivity, where we looked at constraints and how do we satisfy the constraints by making minimal parameter changes. And remember that we talked about making a change to one parameter so that you can think of it as if you have a CPT is a number of distributions, right? And I'm making a change to one of these distributions. That's what happened here. Now, you can talk now about doing multiple parameter changes. So if you have a variable that has 2 parents, and these parents are binary, then that CPT represents 4 different distributions, right? 1 for each instantiation of the parents. You can talk about doing simultaneous changes to these distributions. You can do that actually. And the complexity doesn't change, basically, if you're restricting the changes to the same CPT. And I think that should also be implemented in SAM-IM. If you do multiple CPTs, then it's a different story, and same as multiple constraints. So this could be something that would be interesting to work on. In general, it would be complex because it depends also how many CPTs are involved and how are they related to each other. So you need to be able to characterize the complexity in those cases. Okay, one last thing I want to mention on this segment before we go to the next segment, maybe to motivate also something that we're going to do later. Sometimes when you have multiple changes, as is highlighted here, as we said, you need to get a sense of how small or big these changes in comparison to each other, because all of them may satisfy your constraints, but some of them may perturb the system more than others globally. Then how do you quantify the extent to which they perturb? We're going to tell you about the way to do this later, but in the system you can actually sort them. And it turns out something called log odds. We'll talk about it again later. What we'll do next is talk about this question, which we call here from local to global belief change. That is, I will make a change to a parameter, and I want to get a guarantee on the change that happens to any query, arbitrary query. That's pretty far-reaching. You will see what you can say about this. And again, these results are about a decade old. It took a few decades actually to get these closed forms. From the very first days of using probabilistic reasoning in AI, people were asking these questions. How sensitive are my conclusions or my decisions to the numbers? And the only things people could do initially was just simulations. And once we had these understanding of these graphical models as polynomials, you get a wealth of results. So let's look at it. And here's more concretely. We did this change, remember? We picked this guy here for this variable which has one parent, and we took a parameter, we changed it from 98 to 96. And now I want to ask, can you tell me anything about, give me any guarantee on the change that happens to an arbitrary query, including this one? When you want to address a question like this, you want to say, I made this change to the parameter, and I can guarantee you that any query will not change by that much because of this change. So the starting point is, how do I measure change? And we alluded to this earlier. You can talk about absolute change. You can talk about relative change. You can bound things in using absolute changes. You can show examples where a small absolute parameter change can induce a large absolute query change. Similarly, for the relevant ones, so what can you do? It turns out you can actually bound, and I will give you one, bound the change in a query by the change in a parameter, but it all relies on how do you measure change. And that's going to be the main insight here. And once more, the result will depend on a partial derivative. In this case, we are looking at a conditional query, probability of y given e, that probability, and I'm looking at the partial derivative of that with respect to tau. So here's what we're going to do next. I'm going to show you this partial derivative. It has a nice bound, right? So previously we computed it exactly. Now, I don't want to do inference. The whole point of this is you say, I made this change, tell me something about, give me some guarantee on any conclusions that I have drawn. I want to do this without doing inference. So we're not going to compute this exactly, but we're going to find a bound that is immediately available. You can compute that bound without inference. And then we're going to make a number of observations about this bound to get some sense with regards to this notion of stability, or this notion of when I change a parameter, what happens. So you're going to find it. It's pretty intriguing. And then in the last stage, this bound will be integrated to get some kind of a closed form that ties the change of query to the change of a parameter. Okay? Again, you're going to find beautiful equations. And here it is. Stare at this for a little bit. First of all, it's easy to compute, right? Because what's happening here? I'm talking about a parameter, theta for x given u. So this is the value of the parameter, and this is the value of the negation. I have these immediately. Okay. This is the current value. And what is this? The query. You're looking at some y given e and say, currently it's at 0.8. What can you tell me about it? Or how can it change if I change this parameter that's currently at 0.3? And by just, I'm telling you, tell me what's the current value of the parameter, tell me what's the current value of the query, and I'm already giving you a bound on this derivative. It's pretty remarkable. And look what it tells us. It tells you something very interesting. Here's this guy plotted. This is a bound in terms of two quantities, the current value of the parameter and the current value of the query, correct? So you're varying here the current value of the query, and you're varying here the current value of the parameter. Look what happens. Look for the query. The bound gets smaller as the query becomes extreme, correct? And it's largest when the query is in the middle, 0.5. It's the opposite for the parameters. When you're in the middle, the bound is the lowest. And as you go to extreme parameters, it actually grows. And in a sense, you can think about it this way. The bound approaches infinity for extreme values of the parameter, and it attains the smallest value when the parameter is half. The bound approaches infinity for extreme value, approaches zero for extreme values of the query, and attains its highest value when the query is at half. So you can think of it, extreme queries tend to be robust when changing non-extreme parameters. Yet non-extreme queries may change considerably when changing extreme parameters. You're going to see this even quantified further. The point is, if you're talking about a query that is close to 0 or close to 1 tends to stick. A query that is whose value is around half tend to oscillate more. When you look at parameters, it's kind of the other way around. If you have a parameter around 0.5, then making changes to it does not induce big change. But when you have extreme parameters, then doing changes to them that... Now we're going to take it, the bound, and get more of a closed form. We're going to take it one step further. Okay, here's the secret. When we talked about how do you measure change, we said you could do it absolutely or relatively. We're going to do it actually third way, using odds. You know what odds are. I have a parameter that I'm looking at that is for x given u, correct? And this is the value of the parameter. This is 1 minus. I'm going to compute the odds. Let this denote the odds of variable x given its parent, okay? So that particular parameter that you're about to change, I'm going to take its value over 1 minus the odds. And you're interested in a query. What would that change to the parameter do to the query? I'm also going to look at the query from the point of odds. That is the value of the query over 1 minus. That's the odds of this. This is before I made the change. And now you say I made the change to that parameter. Now I have a new distribution PR prime. I'm going to look at the odds for each one of them as well. And I'm going to call these odds prime, odds prime. We're good so far? So now when I talk about the change in the parameter and how does it impact the change in the query, I'm going to look at in the space of odds and look what happens. There is 2 cases and then they combine nicely in one case. If the change of this guy ends up being positive, you can actually do this. If the change is negative, you can do that. But let me show you the final thing when you put them together. Here is the bound. Stare at it. Here we're talking about the odds after I made the change. This is the query. Y given E is the query, arbitrary query. That's the odds after I made the change. This is the odds before. Log odds, log odds. I'm looking at the difference in the log odds. And what does this say? That cannot be larger than the difference in log odds of the parameters. If you measure change in terms of the change in log odds, you can bound the change in a query. You can say that if I make a change to a parameter, no query will change by more than that. But you have to measure change in terms of log odds as opposed to absolute or relative. I will show you now a concrete application of this, but just to visualize it a little bit more and confirm some of what we seen when we looked at derivative. Look at this illustration. What happened here is I have a query, 0.9, and I'm trying to tell you I want to make a parameter change and tell me, let's say 0.3. By how much I can change a parameter of 0.3 while guaranteeing that this query will stay in this interval. It will not increase or decrease by more than 5%. Make sense? Now, I can give you a parameter that says 0.3. How much can you make change to that to guarantee this? But this does it even more extensively. It tries it for every possible parameter. So we're varying the parameter value from 0 all the way to 1. And what these envelopes are giving you is how much change to keep it within this interval. So you can go that far or that. So as you can see from this, the change you can make to extreme parameters is smaller. As the parameter comes to the middle, then you're allowed to do more. So this is something similar, but look, this is kind of an extreme query. This is not an extreme query. And in a way, we expect it to be a little bit more robust in this case. So I want it to be 55 to 65, and you can see what's going on. But let's look at a concrete example of how you may use this in practice. This is interesting. By the way, this example and part of the material in these slides are in chapter 5, not chapter 16. Chapter 16 is dedicated to the math and all of that, but there was a section in chapter 5 that had a gentle introduction to sensitivity as part of model building. So you'll find the material in both. But let's look at this example. We've seen this network before. We call it the Bayesian network. We have some evidence, E. And here are two queries that you could ask with respect to that network. What is the probability that A is yes, and the answer turned out to be this? And what's the, this is visit to Asia, and this is having cancer, and that turned out to be 25%. The point here is these two queries, one of them is extreme, one of them is not extreme. And now we want to say, okay, I have this parameter, which is the probability of cancer given smoking, and it's currently at 10%. I want to change it to 5%. Can I tell you something about these two guys? These are current values under this parameter value, and I'm changing this to 5%. Can I give you any guarantee on the changes that will take place to these guys? And I don't want to do inference. I want to use this equation that I just showed you to do that. This is two queries, one extreme, one non-extreme, one parameter, and then we're going to follow it by the same thing, except that instead of changing this parameter, which is extreme, we're going to try to change a non-extreme parameter. So now you have 4 combinations, and that gives you a feel of what's going on. So how do you do that? If you look at our equation from before, it had 4 quantities. Log odds for the parameter before and after, log odds for the query before and after. In this case, because I'm changing this guy from 10 to 5, then I have the log odds before and after. For these queries, I have the log odds before, so I have to solve log odds after, and that's what you do here. You just plug in these numbers in that equation and look what you get. This is for the parameter, log odds change for the parameter, and this is for the query. I'm asking about P. I want to solve for this guy. And if you indeed go solve for this guy, what you get is this. It says that if you change your parameter from 10 to 5, I guarantee you this query will remain greater than or equal to that, less than or equal to that. What was it actually? It was 1.17, and now I'm saying it's either this, between this and that. Not bad. No inference. Not bad at all. Let's see the other query, which was around 25%. If you do the same thing, what do you get? You get this. Okay, from the absolute point of view, it's a looser, but we knew this, correct? Intuitively, when we looked at the bounds, we knew that non-extreme queries may change even more. And now let's do the same thing for these two queries, but changing a different parameter. Let's see, the different parameter would be this guy. This is a different parameter, B, yes, given S, yes, that's bronchitis given smoking, which is currently at 60%. So it's non-extreme. And I want to change it to 50%. You do the same thing, like what you get. For the first query, now is what? This to that, tighter. Correct? Which we expect because this is a non-extreme parameter. And similarly for this guy, it's a tighter bound. Once more, pretty interesting that you're doing no inference. It's a fantastic bound. We have one more segment, and it's a short one. We're at our break time. I think it will maybe take less than 10 minutes. So let's just go ahead and do it, and we'll leave early. How about that? Okay, so this last bit, just to give you the little bit of context here. The bottom line is I'm going to give you a distance measure between distributions, and that will allow you to bound the relationship between the distributions. Historically, what happened is, in this work, we were doing this, and then we were getting one great equation after the other, and at some point, you look at things and say, wait a minute, there's probably something fundamental going on. I mean, when the math starts working out so well in so many different contexts, and you start getting similar results, you suspect that what you're seeing are just ramifications or corollaries of a more fundamental result. And that's actually what happened with Dave. Says, no, wait a minute, there's something more serious going on underneath. And this last bit will show you that. It turns out to be, we managed to identify what people call a distance measure. You give me one distribution and another distribution and say, what's the distance between them? There are many distance measures out there, and we proposed one more. And the highlight of the story is, and you see this distance measure is pretty simple. If you come at distribution PR1 and a distribution PR2, and according to the distance measure that we came up with, if you measure the distance and you get a number 0.3, then I immediately use that 0.3 to give you guarantees of the following type. You tell me for the first distance measure, the probability of alpha given beta is this. Then I can tell you if the distance measure between PR1 and PR2 is 0.3, I guarantee you that if you compute the probability of alpha given beta with respect to the second one, it's going to be in this interval. So I can bound the relationship of any query based on that distance measure. And this was the fundamental result. So let's see it. Here's the formula, and I'm going to show it to you pictorially in just a second. Look at it. Stare at this distance measure. It's between two distributions, PR and PR prime, and it has two terms. So what are we doing here? We're iterating over every world, and then looking at what does this distribution say, what does that distribution say for that particular world. Now, you have one of these ratios for every world. So I'm looking at the one that has the highest. And here I'm looking at the minimal, maximum and minimal, and taking the difference between them. It's pretty simple. And this happens to be a true distance measure. When you say distance measure, mathematically you want something called positiveness, symmetry, and triangle inequality, and this guy satisfies these. So it's a proper distance measure, not like the kl-divergence, which was not. Well, let's see it pictorially. ABC is the variables we have. So we have 8 possible worlds. And this is what the first distribution says. Here are the numbers, and here's the second distribution, right? So I'm trying to find the distance between these two guys. Later, this distance measure was called the chan-darwiche measure. You look at the ratio between these two guys, and here they are, right? So what I want to do, I want to find the maximum, the highest, this one, and the smallest happens to be this, and simply take the log difference, and then you get 1.61 for that particular guy. Okay, now look what you can do with this guy. Here it is. If you give me two distributions, PR and PR prime, and arbitrary events alpha and beta, and then you compute the odds of alpha given beta according to the first guy, and then according to the second guy, so you're going to get odds of alpha beta and odds of odds prime, right? If you take the ratio, it is bounded as such. Not bad. Now, this is odds, and people typically think of probabilities, so you can flesh out this and then write a version of this in terms of probability, and it looks like this. If you, same thing, two distributions, PR and PR prime, and you tell me, look, according to the first guy, here's a query, alpha given beta, and this guy says it's P. Can you tell me something about what this guy will say about that same query? Tell you, well, give me the distance. I said the distance is D. What can I say about this? Just fleshing out the previous guy, and you get this. All of these are known quantities. So what you have here on this side and that side is just P and D. That's all you need, and I can actually say something about that guy. The bound is useful when the change is small. Let me see, actually. Yeah. So it gets loose because it's kind of a worst case kind of bound. I mean, you can imagine that, right? If the distance is small, you can get nice bounds. But that's still very useful because we didn't even know that before, right? I mean, if I made a change small, I still want assurance. There was no assurance before. Now I can give you assurance. If you make a big change, this doesn't give you very tight bounds. So this is a distance of 0.1, and this is a distance of 1. And here we're plotting the current value of the query. And what does this say? So 0.1 is pretty not bad, right? It says if the first guy gives a 0.6 to some query, the second guy cannot give it more than this or below that. And now 1, it gets looser, and so on. But let me show you one more property of this distance measure and its practical application. And we will conclude with that. Let's say you have a Bayesian network. That's a distribution, correct? And then you come and say, okay, I computed the probability of alpha given beta according to this Bayesian network, and I got a P, right? Now, you go and make a change to this Bayesian network. You do a parameter change, and you get another network, n prime. That's another distribution. And then you're going to ask the question, what happens to this query? I don't want to do inference. how can I use the distance measure to answer that question? Since this is PR and this is PR prime, if I'm able to measure or compute that distance measure, then I can answer that question. Correct? Question though is it easy to compute that distance measure that I showed you? If you look at the formula, it's trying to look at every possible world and look at the ratios. That's not feasible. Is there an efficient way to do it here? If there is, I can immediately apply it here. And guess what? If the change that you made is to a single CPT, then it's pretty efficient. And here's the result. N prime is obtained from N by changing the CPT for X from this to that. N and N prime induce distributions, this and that. So this is the only change that took place. What can I say about this distance measure between these two guys? You want to guess? Come on, make a guess. This is a distribution. And this is a distribution. Correct? You just look at the distance between these two guys, it is this. So the global distance ends up being the local distance for those that you changed. Fantastic. All of these derivations are in your chapter 16. Do read it and enjoy the math. It's a beautiful example of what one can do when the right formulation is used. Okay, and then now you can do this as we've seen. So let's see a concrete example of it. This is a network that I guess, did we see this one? Maybe not, a version of it, right? So here's an alarm that is triggered by either fire or someone tampering with it. If there's fire, then you see smoke, alarm, people leave the building, and then people leave the building, someone calls reporting that people are evacuating a building. And what happened here is I have this evidence on this guy that there's no smoke and report that people are leaving a building. And if you do this network and compute the probability of fire, you get this in that case, given this evidence. We're good so far? So the idea is someone goes, and here's tampering, and here's currently the prior on tampering. According to this example, this is the CPT. And that's the query. And someone goes ahead and says, I'm going to change this prior to this, right? I changed this to that. Can I say something about the result of this query? And I don't want to do inference. The idea is to do this without inference. What do? Initial network, new network. Initial distribution, new distribution. Let's compute the distance between them. And as we just said, the distance between them is simply the distance between these two guys. You do that distance, you get this number. You apply the formula we talked about, you conclude that this is going to be between this and that. Guaranteed. And the actual answer in this case turns out to be this. No inference. Okay, let me show you one more quick value of this or application, which we've seen before when we talked about ordering changes. You got a bunch of recommendations for how to change distributions, and then the idea was, can I order them in some way? Here's a question for you. I had this distribution here, which corresponded to some prior, and there's two ways to change it, this and that. I ask you, which is a bigger change or smaller change? Okay, it's not that easy, or is it? So one way you can do this is you look at the distance measure between them, right? And if you compute this measure, you are going to find that this is actually much smaller. All right, so pretty much most of what we talked about is implemented in SAM-IAM, which you've already used a little bit for this. You just use it in the simplest form, where you had a query, and then you said, I want it to be greater than. You can use this to, in fact, some of the screenshots did that, to relate two different probabilities. You pick this posterior here and this posterior there, and you say, I want the difference between them to be this, or the ratio and all of that. There's the MPE and ordering, but that's pretty much what we want to say about this subject of chapter 16.